As you may recall, the correlation coefficient measures the strength of a linear relationship between two quantitative variables. The closer it is to either plus or minus 1, the better the least squared regression line will be at making predictions. Now we answer the question, how much of the variability in our response variable can be explained by our explanatory variable? It turns out that the correlation coefficient squared, which is referred to as the coefficient of determination, has the very nice interpretation as the amount of variability in y explained by the linear relationship with x. Returning to our airfare and distance from Baltimore data, there was a strong linear relationship between distance and airfare, with the correlation coefficient being 0.795. Now, if you square 0.795, you get 0.63, which is, as a percent, 63%. This is the coefficient of determination. It says that 63% of the variability in the airfare from Baltimore to other cities can be attributed to the linear relationship with the distance between the cities. This leaves only 37% of the variability in airfare to be explained by factors other than distance. Distance is a very impressive predictor of airfare. To refresh your memory, here again is the age and systolic blood pressure data. And here is the accompanying scatter plot showing a moderate to strong linear relationship. Using StatCrunch, we can get the equation of the prediction line, also called the fitted line. It is always important to interpret the slope clearly and in the context of the data. A slope of 0.97 can be thought of as 0.97 divided by 1. The numerator, 0.97, corresponds to the change in y, in this case systolic blood pressure, and 1 corresponds to the change in age, in x, which in this case is age. So, for each 1-year change in age, the effect is that the systolic blood pressure increases by 0.97 millimeters of mercury. The value of r squared is called the coefficient of determination, and it measures the amount of variability in y that can be explained by the linear relationship with x. The decimal 0.43 is 43%, so 43% of the variability in a person's blood pressure can be explained by the linear relationship with age. All the rest, 57%, of the variability in blood pressure is due to factors other than age. We end by examining a few residuals. Subject number 2 was the outlier in this study. If you recall, there was one data point that was very much above the fitted line. The actual blood pressure of subject number 2 was 220. This 47-year-old person would be expected to have a blood pressure of 144.35. We get this value by substituting 47 into the linear regression equation. The difference between the actual and predicted blood pressure in this case is 75.65, and this is the residual for subject number 2. We interpret this as subject number 2 has a blood pressure that is 75.65 millimeters of mercury higher than would have been expected for a 47-year-old person. Subject number 23, on the other hand, was below the fitted line. Using the same process, we would evaluate his residual as the actual blood pressure of 120 minus the predicted blood pressure of 136, yielding a residual of a negative 16.58. And this indicates that subject 23 has a blood pressure that is 16.58 millimeters of mercury less than would have been expected for a 39-year-old person. Finally, since an extreme amount of emphasis is placed on understanding and interpreting results in this course, we will be using StatCrunch to calculate correlation coefficients, regression slopes, and y-intercepts, and to produce scattered plots with fitted lines.